Jan to all of you. I am Dr. Ritish Kumar and going to represent the topic of noise in PCM system. Subject name is communication engineering. So before starting this topic, we need to understand what is the noise, and let's begin with the university syllabus. So where it lies. So unit number 4, that is based on totally on the pulse PCM system. Here you can clearly see here where it lies the noise consideration in PCM system, right? Again, it lies in the unit number 4, and the book recommended books I preferably refer the book number 1 and book number 3, that is Simon Hatton Communication Systems, John Wiley publisher, while the Tom and Schilling Principle of Communication System. These two books I refer to cover this topic as well. Right. Let's begin the topic noise in the PCN system. Right. So PCM is nothing but a pulse code modulation technique. Where before starting the pulse code modulation techniques, the thing is what is we have to aware about the what is the sampling phenomena. So here I will superficially I will tell you about the what is the sampling theorem or sampling phenomena superficially here. So sampling theorem or sampling phenomena is done to have the digital signal from analog to from analog. So PCM noise in the PCM, as we have the digital signal, so always the digital signal has the low effect over the low effect of the noise over the analog signal as well. So PCM system. If I talk about the noise, right? So in noise in the PCM system, we can have two kind of noise. The first one is the channel noise, as we know, and second one is the quantization noise. Quantization error, we can say, or quantized noise. Right here is channel noise. Channel noise. So in the PCN system, after passing the signal through channel, we have to use the regenerative repeaters. The regenerative repeaters is used to eliminate the channel noise, right? What is the function of regenerative repeater? Also we call RR, right? The regenerative repeater eliminates the channel noise and amplify the signal strength as well. So while using the regenerative repeater after passing the signal through the channel, so we can improve the SNR as well. So channel noise can be removed with the help of RR, while the quantization error or quantization noise cannot be removed after passing through the channel. As we, if you are aware about the PCM system, so here we use the quantizer. So quantizer all converts the discrete signal into the pure digital signal. So after passing after passing the signal through the quantizer, so we have some kind of error to round off the signal, to have the rounding of the signal. So after this kind of error, we can say the quantization noise or quantization error as well. So the thing is, uh, regenerative, right? So we can say the quantization error is an irreversible process. That's why at the receiver side we have nothing to have to eliminate this quantization error as well. So now the thing is, now we need to understand the effect of noise or quantization noise over the PCM signal, right? So let's begin. So I presume that the PSG of the noise, PSG of the quantized noise is looking like this way. Right? Uniform PSG we can treat here plus delta minus delta quantization here F Q Q. This is the PDF of the quantized error. Here we have mentioned here it lies from minus delta to delta. As we know from the property of PDF, the area under the PDF always be equal to 1. It lies from minus delta to delta. You can also minus delta by 2 delta by 2 you can write here. So this total the area under the curve should always be equal to 1. So this value should always be 1 by delta we have, right? So this is the thing that we have here. Now what is the delta here? Delta is the step size. As we know, after quantization process, we have to discretize the total dynamic range within the some certain levels. So this is the step size. Step size is the gap between two consecutive levels that we have in the throughout the quantization level. So this step size formula is V max minus V min divided by total length. As we can see, suppose we have this level V max, this is value is V minimum, this is V max, and we have to if we take n number of levels within this uh, whole dynamic range. So total number of, this is a length we can say, right? So delta for to calculate this is the step size, we can say delta. So this delta is equal to this one, and L is equal to total number of level, that is 2 to the power n. So finally the value of delta is equal to 2 to the power n, right? So by looking this formula, you can clearly observe here, to minimize the step size delta, either you can decrease this dynamic range, right, or increase the number of levels, this one, right? If you want to decrease this step size, then what you have to do here, either you can decrease this total dynamic range, or increase the number of levels. So this is difficult to have, but while to increase the number of levels, it is easier comparable to this to decrease this complete dynamic range. Why we need to decrease the step size? As we know that the quantization error, the maximum quantization error is always equal to plus minus delta by 2. To have the minimum quantization error, we need to have the less value of delta, that is the less value of step size. To have the less value of step size, we need to increase the number of labels. This is the basic concept how you can decrease the quantization error as well. So here I'm considering the PDF of this quantization error that lies in between the maximum value minus delta by 2 delta, and through the definition of the PDF, the area under the PDF should always be equal to 1, and that's why this value would become 1 by delta. I think this one is clear to all of you how it comes, right? So next one is we will drive the signal to quantization noise error, right? Right. If you calculate the total power through this PDF, as we know that what is the total power in terms of random variable. Total power you can calculate by taking the mean square value of the random variable. So here the random variable is QE. So I am taking the QE square. So this is the mean square value. By calculating the mean square value, MSV, we are able to find the total power of the system, that is EQE square. If I so the formula of expectation of EQE square is equal to integration of QE square minus infinity to infinity f QE QE dQE, right? So by using this formula, you can find the total power within the noise PSD, right? So I'm going to calculate. I'm going to drive the noise power, total noise power here. First, we need to remove all these things, right? Let's begin. So, right. So minus infinity to infinity, you can change it from minus delta y to delta y2, and QE square is equal to 1 by delta square, and QE square dQE, right? After applying this limit, after completing this integration process, we have the total noise power, that is represent quantization noise power, and Q is equal to delta square by 12. This is a important one that you have to remember here, right? So you can clearly observe here again, by decreasing the step size, you will have the minimum quantization noise error, right? So now what should be the signal strength? If I calculate the signal to quantization noise ratio, SQNR, that is the ratio of signal power S divided by quantized noise power. What should be the value of signal to quantization noise error ratio, right? So here I am considering the signal that is AM MT is equal to AM cos 2 pi FMT. So the power of this signal is, as we know that the power of the signal is S is equal to AM square by 2, right? And delta is equal to, as we know, So this signal is lying between minus A to, this signal is lying minus A to minus A. So total dynamic range V max by V min is equal to V peak to peak, that is V peak to peak, that is V max minus V min, that is equal to twice A that we have, right? So twice AM you can write. I think now secondly, I am going to remove this section. Right. Twice AM. Now the signal strength that we have S is equal to AM square by 2. So NQ is equal to V peak to peak square divided by 12 into 2 to the power 2n. As we know, delta is equal to V peak to peak divided by the power n, right? So here I am taking this V peak to peak. As we know, V peak to peak is equal to twice AM square divided by 12 cross 2 to the power 2n. So this one is 1 by 3 AM square by 2 to the power 2n. This is the NQ that we have. Now taking the ratio of it, what will we have here? So I think up to this point, right? So S by N equal to S by N, S is equal to AM square by 2 cross N is equal to 3, 1 by 3 into 2 to the power 2n upon AM square. That is cancelled out. So signal to quantization noise ratio is equal to 3 by 2 into 2 to the power 2n. This is important that you have to remember here. Now, if you convert this formula into decibel, then what we will have, that I can write here directly. If you take the decibel value of this, so SQNR in dB is equal to, you can take it, just wait, 1.76 plus 6.02 n, and roughly approximated we can have here 1.8 plus 6n dB. So you can clearly observe here, by increasing the number of levels. Suppose if you increase the number of levels from 1 to 2, there is increment of 1 level. So improvement in the SQNR in the improvement of x square by 6 dB. You can clearly observe 6, and you are positive here. So 6 dB improvement you will have after increasing 1 bit, uh, after increasing the number of levels by 1. If you increase the number of levels by 2, then 12 dB improvement you will have in the SQNR. So this is the signal to quantization noise error, which will you can understand the effect of noise over the signal. So this is all about the signal noise in PCM system, where we have calculated the SQNR. I think this topic is clear to all of you. How you can increase or decrease the SNR by taking the expected value of step size as well. Thank you to all of you. I think this topic is clear to all of you.